Hi everyone, my name is Megan Flynn and I will be going over Chapter 2 from the Concepts of Biology Openstax textbook. If you have not had a chance to access the free textbook, you can do so using that link below at openstax.org/books. So this is the second chapter of this textbook. If you haven't had a chance to look at Chapter 1, I did make a couple videos on that, and the easiest way to find all of those videos is to click the subscribe button so that you can review previous videos I've posted as well as get notified when new videos have been posted. So this chapter is broken up into 3 sections. So I will be going over the first section in this video and then take a look at my other videos for the other 2 sections. So this chapter gets into the chemistry of life. So in the previous chapter, Chapter 1, we took a look at life's hierarchy. So we looked at the atoms make up molecules, molecules make up macromolecules, macromolecules make up organelles, organelles make up organisms, and so forth. So we're going to focus in on the smallest part of life's hierarchy, studying the atoms, and then from there we'll learn how they build molecules. So we're kind of starting at the very beginning here. So this, again, this video covers section 2.1 of the Chapter 2 in the Openstax Concepts of Biology textbook. So we're going to dive into that section. All right, so let's take a look at the learning objectives for this 2.1 section of our textbook. So by the end of this video, you should be able to describe matter and elements, and then also describe the interrelationship between protons, neutrons, and electrons, and the ways in which electrons can be donated or shared between atoms. So this gets into the idea of molecules. Okay, so always a good idea to write those down and then see if you can answer them at the end of the video as kind of a review. Okay. All right, so let's get into, first of all, what is matter? So life is made of matter. Matter is any substance that occupies space and has mass. So you are made of matter. The molecules that are surrounding you right now in the atmosphere are made of matter, okay? The floor that you're sitting on or standing on is made of matter. So life is made of matter, and we're surrounded by matter, anything that occupies space and has mass. So when we're talking about matter, we can basically look at the unique parts of matter. So different unique forms of matter with specific chemical and physical properties are known as elements. And these specific elements, they cannot be broken down into smaller substances by ordinary chemical reactions. So you may have somewhat of an understanding of what elements are if you've ever taken a look at the periodic table. And we're going to get very familiar with the periodic table in this video. But some examples of elements that you've probably heard of would be something like oxygen or hydrogen or carbon, okay? Things like that. These are units of matter, but they pretty much have specific chemical and physical properties that make them different from each other. Okay, so oxygen is different from hydrogen. Hydrogen is different from carbon. So these are unique forms of matter, and we'll talk more about these specific forms of matter throughout this lecture. So these are the elements. Now, when we were talking about life's hierarchy, or the biological hierarchy of life, we talked about atoms being the smallest component there. So atoms, they're the smallest unit of matter that contains all of the elements' chemical properties. So for example, if I'm talking about an oxygen atom, that oxygen atom is going to have all of the properties of the element oxygen. If I'm talking about a hydrogen atom, that hydrogen atom has all of the chemical properties of the element hydrogen, okay? So an atom is just kind of a unit, an actual physical unit of that element that is a piece of matter. So when we're describing an atom, we can actually break it down into two main parts. We have the nucleus, and then we have kind of the surrounding orbit that surrounds the nucleus. And we can take a look inside the atom, in the nucleus of the atom, and we'll notice that there are two parts to it. We have the protons and the neutrons. So the protons, they're going to be housed at the nucleus of the atom. The neutrons will also be housed at the nucleus of the atom. Okay, so the center part. And then surrounding the atom would be where the electrons are found. Okay, so the electrons orbit the nucleus of the atom. Just like you see in this diagram here, this is an example of an atom of helium. And it has 2 protons in the nucleus. It also has 2 neutrons located in the nucleus. And then orbiting the nucleus are 2 electrons. Okay. So this table, actually, I think I got it from a different textbook. I think I got it from the Openstax Biology 2E textbook, but I liked the table, so I'm moving it into our our discussion here. So this one kind of gives you an idea of where everything's located and the charges and the mass of each type in a nice, easy chart to interpret. So I already mentioned that protons and neutrons are found in the nucleus of the atom. Now, the protons, think of protons as positively charged. So one proton has a charge of, it's a positive charge. An electron, those are negatively charged, okay? So you can see how they have opposing charges. So that's why the proton would be in the nucleus, and then the electrons are kind of circulating around it because they can't be right next to each other because of the opposing charges. The neutron, think neutral, okay? So they don't actually have a charge. They're not positive, they're not negative, they're neutral, okay? Now, another thing to note from this chart or from this table is that protons and neutrons, they are heavier than electrons, okay? So if you look over here, we can measure the weight of a proton by its atomic mass unit, or AMU. So protons are 1 atomic mass unit. Neutrons are 1 atomic mass unit. Okay, so they have mass to them. Now electrons, they also have mass to them, but it's such a minute amount that we don't classify it, okay, as having much mass. So we just keep it at 0. It's a little bit above 0, but because it is made of matter, but we will just consider it 0 atomic mass units. Okay, so from this table, we can see that the protons and the neutrons are found in the nucleus of the atom, the center part of the atom, and that's where the mass is. And then that positively charged proton and neutrally charged neutron are in the center, and then the electrons are circulating in the orbit surrounding the nucleus with a negative charge. So going back to an atom, which retains the properties of an element, when we look at an element, we can categorize it by the number of protons it has. So that's what we consider the atomic number. So the number of protons of each element doesn't change. Okay, so for example, if we're talking about oxygen, oxygen has 8 protons. It will always have 8 protons. You'll never see an atom of oxygen that has 9 protons or 7 protons. It always has 8. So that element's atomic number is 8. Okay? Carbon always has 6 protons. It will never have more or less protons. If it has less, then it's a different element. If it has more, it's a different element. So the atomic number is determined by the number of protons. So that does not change. Now remember how the protons and the neutrons are found in the nucleus of the atom. Sometimes we can have different amounts of neutrons found in the nucleus of the atom, but the protons for that particular element will stay the same. So if we have different amounts of neutrons, we have more or less, then we get something called an isotope. So an isotope is the number of basically is from the number of neutrons being variable within an element. So for example, we might have carbon 12, which has 6 protons and 6 neutrons. And so it has a mass number of 12. And I'll get into that in a second. But something like carbon 14 has 6 protons and 8 neutrons. So there's a different number of neutrons compared to a carbon 12. And so because of that, carbon 14 is an isotope. Okay, it has a variable amount of neutrons. So there's various isotopes within an element. Okay. Now, we can determine the mass number by adding up the number of protons and neutrons in the nucleus. Now remember, electrons, we go back, electrons don't have much mass to it, and so we're not counting them in the mass number since their atomic mass is so negligible, it's so small. So if we add up the number of protons and the number of neutrons, we can get the element's mass number. So for example, carbon 12 has 6 protons and 6 neutrons. So 6 plus 6 equals a mass number of 12. If I'm looking at an isotope of carbon, carbon 14 still has 6 protons because that's the atomic number and that doesn't change. But instead it has 8 neutrons. And since it has 8 neutrons, then the mass number is going to be greater. It's going to be 14. Okay, so 6 plus 8 equals 14. So you can see that the element's mass number can vary based on the number of neutrons that are present inside that particular atom that we're talking about. And since there's a number of different isotopes of different elements, we can calculate kind of an average mass number, which we call the atomic mass. So the atomic mass is the mean or the average mass number for all of the naturally occurring isotopes of that particular element. So here's an example. You can see the atomic mass of chlorine. Its chemical symbol is Cl if you want to look it up on a periodic table. The atomic mass number, or the atomic mass, is 35.45. So that's the average of all the different isotopes of chlorine. Okay, so if we look at the mass number of all the different isotopes, we can average it out to about 35.45. So there's different isotopes of chlorine. There's chlorine 35, for example. So 35 is its mass number, by the way, for chlorine 35. And it has 17 protons, which if you look up on the periodic table, the atomic number is 17. And so we know that it always has 17 protons. But it has an extra neutron, so it has 18 total neutrons. So 17 plus 18 equals a total of 35. So the mass number of chlorine 35 is 35, okay? But the atomic number of chlorine in general is 35.45 because we have other isotopes. Here's another isotope, chlorine 37. It has 20 neutrons instead of 18. And so its mass number is 37. So you can see how, the number of neutrons does vary within an element. And so we have to kind of average out the mass number of all of these different isotopes to get the atomic mass. So that's why the atomic mass is usually in a decimal. It's a little different because we're averaging them out. All right. Now, I already mentioned isotopes, so here's the definition in case you didn't write it down earlier. So isotopes are different forms of an element that have the same number of protons but different number of neutrons. So in the previous slide, we saw chlorine-35 has 17 protons but 18 neutrons. Chlorine-38 has 17 protons but 20 neutrons. So you can see that there's a difference in the number of neutrons, but there's always 17 protons because it's chlorine. Chlorine, its atomic number is 17. It always has 17 protons. So an isotope of chlorine would be anything that has a different number of neutrons. Okay, protons stay the same. So in the field of biology, we can actually take advantage of this idea of isotopes, particularly radioisotopes or radioactive isotopes, to help us figure out how old things are. And so a radioisotope or a radioactive isotope, they will emit neutrons or protons and electrons in order to attain a more stable atomic configuration. So for example, carbon-14. Carbon-14 is a naturally occurring radioisotope. It's 14 in the sense that it has 6 protons like carbon-12, but it has 8 neutrons. So it has 2 extra neutrons. And this is a continuous process where we are constantly it's a naturally occurring radioisotope. So it's created in the atmosphere, and it's always being created. So as we develop, we have a relative amount of carbon-14 in our bodies, and it's about equal to the amount of carbon-14 that's in the atmosphere. So right now, your carbon-14 that's in your body is about the same as the atmosphere. But when we die, we're no longer bringing in more carbon-14 because we don't have a respiratory system, we don't breathe, we don't ingest carbon. So the amount of carbon-14 that's it. Okay, we're not getting any more. And carbon-14 is a radioisotope, so it's going to naturally decay. So it's going to decay to something called nitrogen-14. So nitrogen-14 gives off energy in a very, very slow process. And it takes about, if we have 1 gram of carbon-14, it takes about 5,730 years to break that in half. Okay, so 1 gram to 0.5 grams, it would take about 5,730 years in order to decay from carbon-14 1 gram to half a gram of carbon-14. The other half would be this nitrogen-14. Okay, so there's a long half-life. That's what we call half-life. And so we can use this to kind of figure out the age of something that's been dead for a long time. So we can we can analyze, for example, this, pygmy mammoth, and see the ratio of carbon-14 to carbon-12 in its body, and basically knowing that the amount of carbon-14 has a half-life of 5,730 years, we can figure out how old it is, so how long it's been there. So probably about 50,000 years based on this carbon dating. So radioactive isotopes, they will slowly decay over time. And this isn't something, most of them don't happen like really fast. So it takes a long time for carbon-14 to decay to nitrogen-14, for example. Okay. Here's our periodic table. So again, some of you have probably seen this before. You can Google periodic table and you'll see the exact same thing. So this is something that's used all over the world, and it just organizes and displays our different elements. Now, one thing that you'll notice when we take a look at our periodic table of elements, each box contains an element. Okay, so here is one element up here, and we kind of blew it up over there so you can see it better. So notice what's inside of the box. So each box, each element has a symbol. And so we can use that when we're writing out chemical formulas. So for example, water is H2O. So it has 2 hydrogens and 1 oxygen. So instead of writing out water, we write out the chemical formula H2O that signifies that there's 2 hydrogens and 1 oxygen. So it's a lot easier to know the symbol instead of having to write out 2 hydrogens plus 1 oxygen. So that's why we have chemical symbols. And you can see like hydrogen, there's an H. Okay, some of them are single letters like carbon, C, oxygen, O. But something like sodium is Na, okay? Or calcium is Ca. So it's not all just one letter. All right. Now another thing you'll notice in the upper left-hand corner, we have the atomic number. So if you recall, the atomic number is the number of protons in that element. So an atom of hydrogen has 1 proton. An atom of sodium has 11 protons. An atom of oxygen has 8 protons. Okay, and those numbers never change, right? So carbon is always going to have 6 protons. If it doesn't have 6 protons, then it's no longer carbon, okay? So if it has 7 protons, then now it's nitrogen. If it has 5 protons, now it's boron. So the number of protons is the atomic number, and that stays the same for that particular element. The other thing you'll notice is the atomic mass. So remember the atomic mass, it's not going to be usually, a single digit number. So in this case, it's just an average of all the naturally occurring isotopes of hydrogen, their mass numbers averaged out. So we get this atomic mass for hydrogen being 1.008. Okay. Over here, carbon, it's naturally occurring isotopes. If we add up the mass number of all of those, it averages out to about 12.01. Okay, chlorine, we had that example earlier. So chlorine, its atomic mass is 35.45. Okay, so those are the most important things you'll notice about the periodic table, particularly in each element's box. Now we will talk a little bit more about why this is arranged this way in a little bit, but for now, just make sure you can identify the different parts of each element in the periodic table. So what it's describing here. Okay. So here's a review question for you. Magnesium has an atomic number of 12. Which of the following statements is true of a neutral magnesium atom? Is it has 12 protons, 12 electrons, and 12 neutrons? Is it has 12 protons, 12 electrons, and 6 neutrons? Is it has 6 protons, 6 electrons, and no neutrons? Or is it has 6 protons, 6 electrons, and 6 neutrons? So which one of these is true of a neutral magnesium atom? Okay. If you thought it was the first one, I would agree with you. Okay, so in this example, remember the atomic number refers to what? The number of protons. So if the atomic number is 12, it's always going to have 12. Okay, so these 2 answers at the bottom are not going to be correct because, we have 6 protons, that's something else, that's carbon. Okay, so magnesium always has 12 protons. Okay, so these answers. Now it says here that it is neutral. So that means that we have equal amounts of protons to neutrons to electrons. So in this case, we have 12 protons, 12 electrons, and then 12 neutrons. So they're all equal. So that's the correct answer. All right. So let's use the periodic table to help us answer this question. So we have an isotope of sodium. Now sodium, the chemical symbol is Na. So it's over here. It has a mass number of 22. So how many neutrons does it have? So first of all, how do we calculate the mass number? The mass number is the number of protons plus the number of neutrons. So we have the mass number. Now, we can figure out the number of protons by looking at our periodic table. So if we look at Na over here, how many protons does it have? It has 11, right? Because the atomic number is 11. 11 is the number of protons. So now I have the mass number and the number of protons, so I can calculate the number of neutrons. So if the mass number is 22 and mass number is protons plus neutrons, so I have the mass number and the number of protons, I can calculate the number of neutrons by taking that mass number and subtracting the number of protons from it. So what's 22 minus 11? There we go. So there's 11 neutrons in this particular isotope. All right. Now, we know how to figure out the number of protons, the mass number, and so forth from the periodic table of elements. Another useful thing about the periodic table is that it can help us predict how reactive these elements are, okay? Meaning how likely they're going to form chemical bonds with other atoms. So let's take a look at our hydrogen, okay? So hydrogen, it has one proton. Now, if this was a neutral atom of a neutral charge, zero charge atom of hydrogen, then we would have one proton and one electron. Okay. Now, when we're talking about the electron, remember the electron is circulating the nucleus. Okay, so if we have one proton in the center, we have the opposing negatively charged electrons circulating. Okay, in these orbits, the way the electrons are orbiting, okay, they're not going to be static. They're going to be moving around all the time. And where they're moving, it has to do with how much energy there is. Okay, so we have basically an area that's close to the center, the nucleus. That's what we call a shell. And in that shell, we can have a maximum of 2 electrons. Okay, so that innermost shell that surrounds the nucleus can have a maximum of 2 electrons. Then from there, we move out to another shell, okay? So if an element has more than 2 electrons, then the first 2 electrons will occupy the first shell close to the nucleus, and then the remaining electrons may fill the second shell. So the second shell has a maximum of 8 electrons, okay? So I kind of wrote this out for you. So the innermost shell has a maximum of 2 electrons. Next 2 electron shells can have a maximum of 8, okay? And that's basically our octet rule. So that states that with the exception of that first innermost shell that has 2, we have a maximum of 8 in the outermost shell. And that outermost shell is going to determine the reactivity of that particular atom based on how many electrons are present in that outermost shell. So we call that outermost shell the valence shell. Okay, so it has a certain number of electrons and it wants to fill that outermost shell. So if the outermost shell has a maximum of 8 electrons, and it only has 7 electrons, it wants to gain an extra electron to become most stable, okay? So the number of electrons that occupy the outermost shell is going to determine how likely that particular atom is going to want to bond with another to fill its outermost shell. So a molecule are 2 or more atoms chemically bonded together. So first their electrons are going to come together. Now if we go back to this periodic table, we'll look over here at group number 1. So group number 1, if I were to draw out their electron orbitals, or basically their shells, I would see that they always end up with one extra electron in their outermost shell. So for example, lithium has 3 protons. So if it's neutral, it would also have 3 electrons. So the first 2 electrons will fill the innermost shell. And then we have this third electron that's in the second shell. Now that third electron is just sitting there in the second shell, in a shell that can have a maximum of 8. So most likely it wants to get rid of that electron so that it can drop down to its already filled innermost shell. Okay, because that's where it's going to be most stable. Something like sodium, same thing. Okay, sodium has 11 protons, so if it's a neutral sodium atom, it also has 11 electrons. So 2 of its electrons will fill the innermost shell, 8 electrons will fill the second shell. So now we have 10 already accounted for. And then it moves into the third shell where we just have 1 electron. And that 1 electron, that sodium wants to get rid of it so that it can just drop down to its second shell that is already filled, and that way it would be more stable. So it's most likely going to want to get rid of that extra electron. So you can see all the elements over here, they have basically just 1 electron in their outermost valence shell. Over here, group 17, actually let's do group 18 first. So group 18, they are relatively stable. They're known as the noble gases, and it's because they've filled their outermost shells, okay, in just their neutral form. So for example, helium has 2 protons. Helium would then have 2 electrons. And so having 2 electrons, it's filled the innermost shell. And it doesn't have any more electrons, so that's it. So it's filled its innermost shell, or its valence shell. Neon has 10 protons, so think 10 electrons if it's neutral. Neon would have 10 protons, 10 electrons. So the first 2 electrons would go fill the innermost shell, and then the other 8 would fill the second shell, which is its outermost shell, which can hold a maximum of 8. So it's filled its valence shell. And so it doesn't need any extra electrons. It doesn't need to get rid of any electrons. So it's very stable. So we can think of these noble inert gases over here as very stable. And because they're very stable, they're not going to really want to form molecules with other atoms because they don't need to share electrons. They don't need to gain or lose it. They're already happy. They got what they need. But something like chlorine has 17 electrons if it's a neutral atom. So 17 protons, 17 electrons. So the first 2 electrons of the 17 fill the innermost shell. The second 8 electrons fill the second shell, so that's 10. And then we move out to the third shell that can have a maximum of 8, but it only has 7 that can fill it, okay? So because it only has 7 electrons, it really, really wants another electron to fill that valence shell to become more stable. So it wants to react with another atom so that it can get another electron to fill its outermost shell. Okay? So that's another thing that we can notice when we're looking at our periodic table. So groups 1 and 2, okay, they're more likely going to want to lose electrons. Groups 16, 17, they're probably going to want to gain electrons. So we can kind of determine their reactivity based on that. Over here you can see that groups 1 and 17 are more likely to form an ion. So an ion is basically an atom that is the amount of protons, or the ratio to protons to electrons, is not equal. So if they have an extra proton, then they're going to be positively charged. So it's a positively charged ion. If they have an extra electron, then they would be negatively charged. Okay, so for going back to our example of group 1, remember how something like lithium has 3 protons. If it's a neutral atom, then it also has 3 electrons. So the first 2 electrons fill the innermost shell, and then it just has 1 electron circulating its valence shell. And because of that, it wants to get rid of it so it can just drop down to a more stable form. So it wants to get rid of that extra electron. If it got rid of the extra electron, it would only have 2 electrons, but 3 protons. So because of that, now we have a positively charged ion of lithium. Over here, we have fluorine. Fluorine has 9 protons, so if it's a neutral atom of fluorine, it would also have 9 electrons. So the first 2 electrons fill the innermost shell. The next 7 almost fill the second shell, but it just needs 1 more to fill it to be very, very stable. So it's going to want to gain an extra electron. So if it ends up gaining an extra electron, instead of 9 electrons, it now has 10. So we have 9 positively charged protons, but 10 negatively charged electrons, so we end up as an ion with a negative charge. Okay, so ions, they gain or lose their electrons in order to fill their outermost shells. So we can use this periodic table to predict which ones are more likely to form ions. Okay, so usually the guys over here and the ones over in this area. But remember, 18, those are the inert gases that are stable. They've already filled their shells, so they're not going to be reactive at all. So now that we have an understanding of why atoms are going to want to form bonds to fill their outermost shells, we're going to kind of show that in another visual. Now, we can see here's sodium. Now, you can see the electron placement a little bit better in this example. If I go back to our previous slide looking at the periodic table, here's sodium over here. So a neutral sodium atom has 11 protons and 11 electrons. So if we move over here, this is how the electrons are displayed. So remember, the innermost shell always has 2, so there's 2, a maximum of 2. And then the second shell has a maximum of 8. And then octet rule, the third shell has a maximum of 8. So this one has 11 electrons. So there's 2 in the first shell, 8 in the second shell, and then it just has 1 in the third shell. So this sodium atom really doesn't want to have just 1 electron circulating in its outermost shell. It kind of wants to get rid of it so that it drops down to having the second shell as its valence shell. So it wants to get rid of that extra electron. And when it does so, then it becomes an ion, right? Over here, chlorine, let's go back and look. Chlorine has 17 protons, so if it's a neutral atom, it would have 17 electrons. The first 2 electrons fill the innermost shell, then we have 8 fill the second shell, and then we have 7 filling the third shell. So it just needs 1 more to fill its valence shell. So it really wants to get an extra electron and become an ion, okay? So hey, why does it sodium that wants to get rid of an electron? Maybe it can get together with chlorine that wants to gain that electron. And so when we see this happening, you can see this kind of transfer of electrons, okay? So they're gonna form a chemical bond where we have this sodium got rid of its electron and chlorine gained that electron. Okay, so since not all elements have enough electrons to fill their outermost shell, they're going to form a chemical bond. Okay, so that way they can stabilize or reach that stable outermost shell. And so here we have a molecule. So we have 2 or more atoms chemically bonded with each other, resulting in a molecule. Okay. So just going back and kind of adding some more vocabulary on it. When we have a positive ion, meaning that there is an extra, we have more protons than electrons in that particular atom, we call those ions cations. Okay? And we already know how they're formed by losing electrons. So if they get rid of an electron, they end up with more protons than electrons, just like our sodium over here. So sodium, when it has lost its outermost electron, it becomes a cation, okay, a positively charged sodium ion. An anion is a negatively charged ion, okay? So here chlorine has gained that extra electron, so now it has more electrons than it does protons, so it's negatively charged. And so it's an anion. And the transfer of that electron is basically, hey, it's known as electron transfer, movement of electrons from one element to another. And in this case, this bond that is formed between these two atoms, this chemical bond, is known as an ionic bond. So an ionic bond is when we have two atoms, two ions. Basically, they're going to be transferring electron between each other. So one loses the electron, becomes a cation, the other gains the electron because it becomes an anion. So they form an ionic bond. So cation, sodium, and anion, chlorine, have formed an ionic bond. Okay. So ionic bonds, by the way, are what we consider kind of relatively weak bonds because, you know, once the sodium has gotten rid of its electron, it's pretty happy, okay? Another type of bond could be where instead of just gaining or losing an electron, maybe two atoms can share the electrons. And when they're sharing the electrons, they're so close together that the electrons from their outermost shells will be shared. And that allows them to become relatively stable. And so we call those type of bonds covalent bonds. So covalent bonds, they're sharing the electrons. Okay, so we end up with, actually there's two types of covalent bonds. One is a polar covalent bond, and the other is called a non-polar covalent bond. So a polar covalent bond means that we have two atoms, they're sharing electrons, but one of them holds on to that electron more often in its outermost shell compared to the other. So it ends up being an unequal sharing of electrons. So here's an example. We have an oxygen atom, and oxygen, they have, if it's neutral, it has 8 protons, or its atomic number is 8. So it has 8 protons, 8 electrons. So the first two electrons will fill the innermost circle, innermost orbit. Then it has 6 in its valence shell. Since it has 6, it wants 2 more to fill. So it can bond with 2 hydrogen atoms. Because hydrogen, if you recall, hydrogen has, its atomic number is 1, so it has 1 proton. If it's neutral, then it also has 1 electron. So it only has 1 electron circulating the nucleus, but it really wants 2 to fill its outermost shell. So since this hydrogen wants 2, it can kind of share with oxygen. Okay, so oxygen wants to gain gain 2 electrons. Hydrogen wants to gain an electron to fill its outermost shell. So they'll share the electrons. The problem is oxygen tends to be kind of, you know, more electronegative, and so it's going to house that electron that it's sharing. So the electron that should be circulating hydrogen, it's sharing it, right? And so it's going to occur, that electron occurs more often in the oxygen's outermost shell. And because of that, we end up with a slightly negative charge to the oxygen end of this molecule. And then because hydrogen doesn't always get the electrons circulating its outermost area, then it's going to end up being a little bit more positive on this side of the molecule. Okay, so that symbol right there means partial positive. It's not a complete positive, it's not like an ion. It just because sometimes that electron will swing over and come back to the hydrogen. So they're sharing the electrons. Sometimes it's over here, sometimes it's over here. When it's over here, it's going to be more often of the time. That means that we end up with this water molecule that has a slightly negative end to the oxygen side and a slightly positive end to the hydrogen sides. And so we call that polar covalent bonds. Now a non-polar covalent bond means that they are equally sharing. So carbon has 6 protons, so if it's neutral it has 6 electrons. 2 will fill the first shell, and then it has 4 in its outermost shell. Because it has 4, it wants 4 more to fill its outermost shell. So it's going to form these nonpolar covalent bonds. So here you can see a nonpolar covalent bond with 4 hydrogens. So each of these hydrogens, they need an extra electron to fill their outermost shell, and so they might as well just share it. Okay, so they can kind of share them. And so by sharing them, this becomes a more stable carbon, more stable hydrogen. They're linked together in a strong bond, holding them together in this covalent bond. And because it's equally sharing, the electron is going to be equally over on the hydrogen side versus the carbon side, then it's considered a nonpolar covalent bond. All right? So think polar covalent bond, unequal sharing. Nonpolar, equal. All right? So here's another example of a nonpolar covalent bond. We have oxygen, 2 oxygen atoms. They're going to form a double bond, so they're going to share their electrons with each other at the same rate. So you see 2 lines there, that means a double bond. So they're actually sharing a total of 4 between them. So we talked about covalent bonds. They're sharing electrons, so they're very, very strong bonds. Ionic bonds, you either gain or lose an electron, so it's a weaker bond. Now the other 2 that we describe in biology are hydrogen bonds and van der Waals interactions. So in hydrogen bonds are weak interactions, so it's not a strong bond, between the hydrogen's partial positive end from one molecule and a partially negative charge from a nearby other molecule. So here's an example. Now this is water. This is a water molecule. Remember, water molecules, they have a polar covalent bond. Okay, so the oxygen end has a partially negative charge. The hydrogen ends have a partially positive. Since this hydrogen is less likely to get, its own electron, it's most likely going to be orbiting the oxygen, it's going to be partially positive. But it, will be more attracted to partial. If you're positive, you're going to be more attracted to negative, okay, in this case. So this hydrogen might form a hydrogen bond with another water molecule, the partially negative end of that other water molecule. Okay, so we have a partially positive end of hydrogen and then this partially negative end of a nearby oxygen molecule, and they form a weak interaction between them. Okay, it's easily broken. It's not a strong bond like what's holding the hydrogen to the oxygen in the water molecule itself. These are weak interaction between 2 water molecules. Okay, so those are hydrogen bonds. And then finally, the last one, van der Waals interactions. Those are very, very weak interactions between molecules due to temporary charges attracting atoms that are very close together. So in a van der Waals interaction, we don't really talk too much about it, but sometimes when we have the electrons moving around the nucleus, we can have a temporary partial charge formed when the electrons are being shared by something else. And because of that, just that temporary partial charge could cause some weak interaction with another nearby molecule with a partial charge. Okay? All right, so let's finish off with this question here. So which type of bond represents a weak chemical bond? Would it be considered a hydrogen bond, an ionic bond, a covalent bond, or a polar covalent bond? Well, first off, we can kind of eliminate two answers right off the bat, because we know that covalent bonds, they're strong because they're sharing electrons to fill their outermost shell. So they don't want to, one of them to go off and separate, because then they can't share those electrons. They can't fill their outermost shell. So covalent bonds and polar covalent bonds, they're strong. So they're not going to be the answer there. So now we're between ionic and hydrogen. So remember, an ionic bond is where we have a bond between two oppositely charged ions. So we have the sodium, for example, that is a cation that wants to get rid of an electron. The chlorine wants to gain that electron. So in order to do so, they're going to be coming close enough to be able to see that electron transfer take place. Okay, so that is a bond, and it's a relatively weak bond, okay, but it's not as weak as a hydrogen bond. So hydrogen bond is where we have the partially positive end of a hydrogen atom that's already in a molecule to a partially negative end of a nearby molecule. So they're not going to be connected for very long. They're just a weak interaction. So hydrogen bonds would be the weakest form. They're just kind of attracted to each other, but they're not transferring electrons. So hydrogen bonds are considered the weakest of these examples here. All right, so by now we've already described matter and elements. We've described the interrelationship between protons, neutrons, electrons, and the way in which electrons can be donated or shared between atoms. So so the next video is going to cover the second section of chapter 2, where we deal with water itself. So remember, water, that molecule, has polar covalent bonds, but it can form hydrogen bonds with nearby water. So we're going to describe the properties of water and why they become so essential to life in our next video, 2.2 water. So always a good idea to click that subscribe button so that you can easily find this next video when it comes out.